ਕਿਸੇ ਕੈਮੀਕਲ ਰਿਐਕਸ਼ਨ ਦੀ ਰੇਟ ਉੱਤੇ ਟੈਂਪਰੇਚਰ ਦਾ ਕੀ ਪ੍ਰਭਾਵ ਪੈਂਦਾ ਹੈ? ਆਓ ਇਸ ਐਨੀਮੇਸ਼ਨ ਦੀ ਸਹਾਇਤਾ ਨਾਲ ਇਸ ਨੂੰ ਸਮਝੀਏ। ਅਸੀਂ ਦੋ ਕੰਟੇਨਰ ਵੇਖ ਰਹੇ ਹਾਂ ਜਿਨ੍ਹਾਂ ਵਿੱਚ ਬਰਾਬਰ ਮਾਤਰਾ ਵਿੱਚ A2 ਅਤੇ B2 ਮੋਲੀਕਿਊਲਸ ਹਨ। ਅਸੀਂ ਵੇਖ ਰਹੇ ਹਾਂ ਕਿ ਇੱਕ ਦੂਜੇ ਕੰਟੇਨਰ ਦੇ ਹੇਠ ਬਰਨਰ ਰੱਖਿਆ ਗਿਆ ਹੈ। ਪਹਿਲੇ ਕੰਟੇਨਰ ਵਿੱਚ ਮੋਲੀਕਿਊਲਸ ਦੀ ਸਪੀਡ ਕਾਫੀ ਘੱਟ ਹੈ, ਜਦਕਿ ਦੂਜੇ ਕੰਟੇਨਰ ਵਿੱਚ ਉਹ ਕਾਫੀ ਤੇਜ਼ੀ ਨਾਲ ਗਤੀ ਕਰਦੇ ਹਨ। ਇਸੇ ਤਰ੍ਹਾਂ ਅਸੀਂ ਵੇਖ ਰਹੇ ਹਾਂ ਕਿ ਦੂਜੇ ਕੰਟੇਨਰ ਵਿੱਚ ਪਹਿਲੇ ਕੰਟੇਨਰ ਦੇ ਮੁਕਾਬਲੇ ਮੋਲੀਕਿਊਲਸ ਦਰਮਿਆਨ ਟਕਰਾਅ ਜਾਂ ਕੋਲੀਜ਼ਨਸ ਕਾਫੀ ਤੇਜ਼ੀ ਨਾਲ ਹੋ ਰਿਹਾ ਹੈ। ਇਸ ਤਰ੍ਹਾਂ ਬੜੀ ਛੇਤੀ ਹੀ ਇਹ AB ਕੰਪਲੈਕਸ ਬਣਾ ਲੈਂਦੇ ਹਨ, ਜਦਕਿ ਪਹਿਲੇ ਕੰਟੇਨਰ ਵਿੱਚ ਮੋਲੀਕਿਊਲਸ ਕੰਪਲੈਕਸ ਬਣਾਉਣ ਲਈ ਬਹੁਤ ਜ਼ਿਆਦਾ ਸਮਾਂ ਲੈਂਦੇ ਹਨ। ਇਹ ਵੇਖਿਆ ਗਿਆ ਹੈ ਕਿ ਜਦੋਂ ਕਿਸੇ ਕੈਮੀਕਲ ਰਿਐਕਸ਼ਨ ਵਿੱਚ ਟੈਂਪਰੇਚਰ ਦੀ ਵਰਤੋਂ ਕੀਤੀ ਜਾਂਦੀ ਹੈ ਤਾਂ ਮੋਲੀਕਿਊਲਸ ਦੀ ਗਤਿਜ ਊਰਜਾ ਯਾਨੀ ਕਾਇਨੈਟਿਕ ਐਨਰਜੀ ਵੱਧ ਜਾਂਦੀ ਹੈ। ਇਸ ਦਾ ਮਤਲਬ ਹੈ ਕਿ ਪਰ ਯੂਨਿਟ ਟਾਈਮ ਉੱਤੇ ਨੰਬਰ ਆਫ ਕੋਲੀਜ਼ਨਸ ਵਿੱਚ ਵਾਧਾ ਹੁੰਦਾ ਹੈ। ਸਿੱਟੇ ਵਜੋਂ ਪ੍ਰੋਡਕਟ ਫਾਰਮੇਸ਼ਨ ਦੀ ਪ੍ਰਕਿਰਿਆ ਪੂਰੀ ਹੋ ਜਾਂਦੀ ਹੈ।
Hello students, our today's point of discussion is activation energy. Before starting our discussion on it, first let's see what are the learning objectives of today's topic.
After completion of this topic, learners will be able to discuss effect of temperature on the chemical reaction, define activation energy, derive formula for activation energy, solve numerical problems, discuss activation energy in detail. Effect of temperature on the chemical reaction. ਆਓ ਇੱਕ ਵਾਰ ਫੇਰ ਉਦਾਹਰਨ ਦੀ ਸਹਾਇਤਾ ਨਾਲ ਕੈਮੀਕਲ ਰਿਐਕਸ਼ਨ ਦੀ ਦਰ ਤੇ ਟੈਂਪਰੇਚਰ ਦੇ ਪ੍ਰਭਾਵ ਨੂੰ ਸਮਝੀਏ। ਆਓ ਆਕਜ਼ੈਲਿਕ ਐਸਿਡ ਅਤੇ ਪੋਟਾਸ਼ੀਅਮ ਪਰਮੈਂਗਨੇਟ ਦੇ ਵਿੱਚ ਕੈਮੀਕਲ ਰਿਐਕਸ਼ਨ ਵੇਖਦੇ ਹਾਂ। ਆਕਜ਼ੈਲਿਕ ਐਸਿਡ ਅਤੇ ਪੋਟਾਸ਼ੀਅਮ ਪਰਮੈਂਗਨੇਟ ਦੇ ਮਿਕਸਚਰ ਨੂੰ ਟੈਸਟ ਟਿਊਬ ਵਿੱਚ ਲਿਆ ਗਿਆ ਹੈ। ਆਓ ਦੋ ਟੈਸਟ ਟਿਊਬਾਂ ਲਈਏ ਜਿਨ੍ਹਾਂ ਦੋਹਾਂ ਵਿੱਚ ਬਰਾਬਰ ਮਾਤਰਾ ਵਿੱਚ ਪਰਪਲ ਰੰਗ ਦਾ ਸੋਲੂਸ਼ਨ ਹੈ। ਜਿਸ ਤਰ੍ਹਾਂ ਕਿ ਤੁਸੀਂ ਵੇਖ ਰਹੇ ਹੋ, ਪਹਿਲੀ ਟੈਸਟ ਟਿਊਬ ਨੂੰ ਟੈਸਟ ਟਿਊਬ ਸਟੈਂਡ ਵਿੱਚ ਰੱਖਿਆ ਗਿਆ ਹੈ ਅਤੇ ਦੂਜੀ ਟੈਸਟ ਟਿਊਬ ਜੋ ਕਿ ਇੱਕ ਬੀਕਰ ਵਿੱਚ ਵਿਖਾਈ ਦਿੰਦੀ ਹੈ, ਉਸ ਨੂੰ ਬੀਕਰ ਸਮੇਤ ਬਰਨਰ ਦੇ ਉੱਪਰ ਟ੍ਰਾਈਪੋਡ ਸਟੈਂਡ ਤੇ ਰੱਖਿਆ ਗਿਆ ਹੈ। ਆਓ ਵੇਖੀਏ ਕਿ ਦੂਜੀ ਟੈਸਟ ਟਿਊਬ ਦੇ ਸੋਲੂਸ਼ਨ ਵਿੱਚ ਕੀ ਹੁੰਦਾ ਹੈ। ਦੂਜੀ ਟੈਸਟ ਟਿਊਬ ਦੇ ਬਰਤਨ ਨੂੰ ਜਲਾਇਆ ਜਾਂਦਾ ਹੈ। ਇਨੀਸ਼ੀਅਲੀ ਟੈਂਪਰੇਚਰ 20 ਡਿਗਰੀ ਸੈਲਸੀਅਸ ਨਾਪਿਆ ਗਿਆ। 10 ਮਿੰਟ ਦੇ ਬਾਅਦ ਇਹ ਵੇਖਿਆ ਗਿਆ ਕਿ ਟੈਂਪਰੇਚਰ 20 ਤੋਂ 40 ਡਿਗਰੀ ਸੈਲਸੀਅਸ ਤੱਕ ਪਹੁੰਚ ਗਿਆ। ਅਸੀਂ ਦੂਜੀ ਟੈਸਟ ਟਿਊਬ ਵਿੱਚ ਵੇਖਦੇ ਹਾਂ। ਇਸ ਵਿਚਲੇ ਸੋਲੂਸ਼ਨ ਦਾ ਕੀ ਰੰਗ ਗਾਇਬ ਹੋ ਰਿਹਾ ਹੈ? ਪਹਿਲੀ ਟੈਸਟ ਟਿਊਬ ਦੇ ਸੋਲੂਸ਼ਨ ਵਿੱਚ ਕੀ ਹੁੰਦਾ ਹੈ? ਇੱਥੇ ਰੰਗ ਵਿੱਚ ਕੋਈ ਤਬਦੀਲੀ ਨਹੀਂ ਹੋਈ ਹੈ। ਇਸ ਦਾ ਮਤਲਬ ਹੈ ਕਿ ਇਸ ਵਿੱਚ ਕੋਈ ਰਿਐਕਸ਼ਨ ਨਹੀਂ ਹੋਇਆ।
Why a reaction occurs? What is the reason behind a chemical reaction to be completed? Let's discuss. For a reaction to occur, reactants must collide with each other. As we prepare ourselves before examinations and try to complete our notes and studies to be successful in the examinations, similarly, reactant molecules collide with each other for the completion of a chemical reaction. But all collisions are successful in reactants? No, it is not so. Only those collisions result in product formation which have energy equal or more than a certain minimum energy. It means that there is a condition for product formation. There is a boundary line which is known as minimum energy level. There can be three situations. It is important to know about them. These are: if reactants have energy equal to this minimum energy level, they will combine to form products. If reactants have energy more than this minimum energy level, they will combine to form products. And last, if reactants have energy less than this minimum energy level, they will not combine to form products. So, students, it must be clear to you that product formation is possible only in 1 and 2 situations, but in situation 3, product formation is not possible. Students, there is one more name for this minimum energy level. Do you want to know? Let's try to know. This energy is also known as the threshold energy. This implies that there is an energy barrier between reactants and products which must be crossed before products can be formed. विद्यार्थियों, मैनू पता है कि तुहाडे मन विच एक सवाल उठ रहा है। ਇਹ सवाल की है मैं ਤੁਹਾਨੂੰ ਦੱਸਦੀ ਹਾਂ। ਪ੍ਰਤੀਕਾਰਕਾਂ यानी रिएक्टेंट्स ਨੂੰ ਪ੍ਰੋਡਕਟਸ ਬਣਾਉਣ ਲਈ ਥ੍ਰੈਸ਼ੋਲਡ એનર્ਜੀ ਦੀ ਜ਼ਰੂਰਤ ਹੁੰਦੀ ਹੈ। ਇਹ ਸਹੀ ਹੈ, ਪਰ ਰਿਐਕਟੈਂਟਸ ਵਿੱਚ ਇਸ ਥ੍ਰੈਸ਼ੋਲਡ એનર્ਜੀ ਦਾ ਸੋਰਸ ਕਿਹੜਾ ਹੈ? ਇਹ ਜਾਣਨ ਦੀ ਕੋਸ਼ਿਸ਼ ਕਰਦੇ ਹਾਂ। ਉਹ એનર્ਜੀ ਜੋ ਰਿਐਕਟੈਂਟਸ ਨੂੰ ਪ੍ਰੋਡਕਟਸ ਬਣਾਉਣ ਲਈ ਚਾਹੀਦੀ ਹੈ, ਪ੍ਰਤੀਕਿਰਿਆ ਕਰਨ ਵਾਲੇ ਅਣੂਆਂ ਦੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਤੋਂ ਆਉਂਦੀ ਹੈ। ਆਓ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਦੀ ਦੁਹਰਾਈ ਕਰਦੇ ਹਾਂ। ਕਿਸੇ ਵੀ ਵਸਤੂ ਦੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਉਹ ਐਕਸਟਰਾ એનર્ਜੀ ਹੈ ਜੋ ਕਿ ਇਸ ਦੀ ਗਤੀ ਦੇ ਕਾਰਨ ਪ੍ਰਾਪਤ ਕੀਤੀ ਜਾਂਦੀ ਹੈ। ਆਓ ਇਸ ਦੀ ਡੈਫੀਨੇਸ਼ਨ ਜਾਣਦੇ ਹਾਂ। ਇਸ ਨੂੰ ਇਸ ਤਰ੍ਹਾਂ ਡਿਫਾਈਨ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ ਕਿ ਕਿਸੇ ਦਿੱਤੇ ਹੋਏ ਮਾਸ ਵਾਲੀ ਬੋਡੀ ਨੂੰ ਇਸ ਦੀ ਸਥਿਰ ਅਵਸਥਾ ਤੋਂ ਗਤੀਸ਼ੀਲ ਅਵਸਥਾ ਵਿੱਚ ਲੈ ਜਾਣ ਲਈ ਕੀਤੇ ਗਏ ਕੰਮ ਨੂੰ ਇਸ ਦੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਕਹਿੰਦੇ ਹਨ। It means the work needed to accelerate a body of a given mass from rest to its current velocity. What is activation energy? The minimum extra energy over and above the average potential energy of the reactants, which must be supplied so that the reactants are able to cross over the energy barrier, is called the activation energy. Activation energy is represented by EA. Which formula is used to calculate activation energy? Answer is activation energy is equal to threshold energy minus average energy of the reactants. If we represent threshold energy by ET and average energy by ER, we can write activation energy is equal to threshold energy minus average energy of the reactants. If we represent activation energy by EA, threshold energy by ET and average energy by ER, we can write EA is equal to ET minus ER. What is the role of activation energy in chemistry? Let's try to know it with the help of its definition. The activation energy in chemistry is the energy needed by a system to initiate a particular process. Students, we are studying activation energy. Do you know what are the uses of activation energy? Activation energy is often used to denote the minimum energy needed for a specific chemical reaction to occur. Students, I am asking you a question. Try to answer it. For the completion of a reaction and for product formation, collision is essential between reacting molecules. It is clear to you? Try to answer. Are all collisions between reacting molecules are fruitful for product formation? No, it is not true. All collisions are not fruitful. आओ विचार करिए क्यों। दो मॉलिक्यूल्स विच रिएक्शन होने ਲਈ मॉलिक्यूल्स ਦਾ ਕਰੈਕਟ ओरिएंटेशन विच कोलिजन ਜ਼ਰੂਰੀ ਹੈ ਅਤੇ ਉਹਨਾਂ ਮੋਲੀਕਿਊਲ ਕੋਲ ਮਿਨੀਮਮ ਅਮਾਉਂਟ ਆਫ એનર્ਜੀ ਹੋਣੀ ਚਾਹੀਦੀ ਹੈ। ਅਸਲ ਵਿੱਚ ਕੀ ਵਾਪਰਦਾ ਹੈ, ਮੋਲੀਕਿਊਲ ਕੀ ਬਣਤਰ ਲਈ ਦੋ ਪਰਮਾਣੂ ਇੱਕ ਦੂਜੇ ਦੇ ਨੇੜੇ ਆਉਂਦੇ ਹਨ, ਜਿਸ ਦੇ ਨਤੀਜੇ ਵਜੋਂ ਉਹਨਾਂ ਦੇ ਇਲੈਕਟ੍ਰੋਨ ਕਲਾਉਡ ਇੱਕ ਦੂਜੇ ਨੂੰ ਰਿਪੈਲ ਕਰਦੇ ਹਨ। एक chemical reaction which product बनाउन ਲਈ ਪ੍ਰਤੀਕਾਰਕਾਂ यानी reactants ਨੂੰ activation energy ਦੀ ਲੋੜ ਹੁੰਦੀ ਹੈ। ਇਸ એનર્ਜੀ ਦਾ ਸੋਰਸ ਕੀ ਹੈ? ਇਹ એનર્ਜੀ ਕਿੱਥੋਂ ਆਉਂਦੀ ਹੈ? ਐਕਟੀਵੇਸ਼ਨ એનર્ਜੀ ਸਿਸਟਮ ਦੀ ਹੀਟ ਤੋਂ ਆਉਂਦੀ ਹੈ। ਕੀ ਹੁੰਦਾ ਹੈ ਜਦੋਂ ਰਿਐਕਟੈਂਟ ਸਫੀਸ਼ੀਐਂਟ એનર્ਜੀ ਹਾਸਲ ਕਰਦੇ ਹਨ ਤਾਂ ਇਲੈਕਟ੍ਰੋਨ ਕਲਾਉਡਸ ਦੇ ਦਰਮਿਆਨ ਰਿਪਲਸ਼ਨ ਘਟ ਜਾਵੇਗੀ। ਨਤੀਜੇ ਵਜੋਂ ਮੋਲੀਕਿਊਲਸ ਦਰਮਿਆਨ ਖਿੱਚ ਦੇ ਕਾਰਨ ਮੋਲੀਕਿਊਲਸ ਇੱਕ ਦੂਜੇ ਦੇ ਬਹੁਤ ਨੇੜੇ ਆ ਜਾਂਦੇ ਹਨ। ਆਖਿਰ ਵਿੱਚ ਇਹ ਦੁਬਾਰਾ ਰੀਅਰੇਂਜ ਹੋ ਕੇ ਪ੍ਰੋਡਕਟ ਬਣਾਉਂਦੇ ਹਨ। Let's take an example. Chemical reactions ordinarily occur as a result of collisions between reacting particles. Let's consider a chemical reaction. Carbon monoxide in gaseous state reacts with nitrogen dioxide in gaseous state to form carbon dioxide and nitric oxide in gaseous state. Rate is equal to K multiplied by concentration of nitrogen dioxide raised to the power 2. The rate of the reaction is independent of concentration of carbon monoxide. Doubling the concentration of nitrogen dioxide increases the rate of the reaction by 4 times. Students, we have discussed about activation energy. Do you know? Each reaction has a characteristic value of energy of activation. Yes, it is so. Let's assume that there are two chemical reactions to proceed. A chemical reaction has comparatively low activation energy than another chemical reaction at a given temperature. What will happen? What will be the impact of these differences in activation energy on the rate of a chemical reaction? Yes, in this case we find that at a given temperature, a reaction with low activation energy will proceed faster than a reaction with high energy of activation. How is it possible to determine it? Is there any method to find it? Absolutely correct. This can be easily determined from the Arrhenius equation. Let's consider a chemical reaction. M plus N gives P. In this chemical reaction, M and N are reactants and P is product. Let's plot a graph showing plot of potential energy versus reaction coordinate. Look at this animated chart. Potential energy is plotted against reaction coordinate. Potential energy is taken on y-axis. Reaction coordinates has been taken along x-axis. Energy barrier is also shown here. Let's assume that reactants are present at X point, whereas products are present at Y point. It is calculated that activation energy of reactants is higher than that of products. Value of activation energy of reactants is shown here with the help of animated line. Value of activation energy of products is also shown here with the help of animated line. Activation energy graph for all over reaction is also shown here. Activation energy difference between reactants and products is also shown here. Let's try to know activation energy for fast and slow chemical reactions. What is the value of activation energy for fast reactions? Answer is activation energy is low for fast reactions. What is the value for activation energy for slow reactions? And the answer is activation energy is high for slow reactions. A potential energy diagram for an endothermic reaction is shown here. Reaction coordinates are taken along x-axis. Potential energy is taken along y-axis. What happens if the potential energy of the products is greater than that of reactants? The amount of energy released in going from an activated complex to products will be less than the activation energy. The reaction will be endothermic. When two reactants A and B-C combine, they form a transition state or activated complex, which decomposes to give the products. This is also explained in transition state or activated complex theory. What will happen in a chemical reaction if the temperature is raised by 10 degrees Celsius in a chemical reaction. It has been calculated that for a chemical reaction with rise in temperature by 10 degrees Celsius, the rate constant is nearly doubled. Temperature coefficient. The ratio of rate constants of a reaction at two different temperatures differing by 10 degree is known as temperature coefficient. Mathematically, it is also shown here. Temperature coefficient is equal to K 35 degree upon K 25 degree, which is again equal to K 308 upon K 298, which is again equal to 2 or 3 times. It is amazing. Let's have a look on the Arrhenius equation.
ਆਓ ਇਸ ਐਨੀਮੇਸ਼ਨ ਰਾਹੀਂ ਕੈਮੀਕਲ ਰਿਐਕਸ਼ਨ ਦੀ ਸੋਲੂਬਿਲਿਟੀਜ਼ ਉੱਤੇ ਟੈਂਪਰੇਚਰ ਦੇ ਪ੍ਰਭਾਵ ਨੂੰ ਦੇਖੀਏ। ਵਿਦਿਆਰਥੀਓ, ਆਓ 5 ਟੈਸਟ ਟਿਊਬਾਂ ਲਈਏ ਅਤੇ ਉਹਨਾਂ ਦੇ ਉੱਪਰ T1, T2, T3, T4 ਅਤੇ T5 ਦੇ ਨਿਸ਼ਾਨ ਲਾਓ। ਇੱਥੇ ਅਸੀਂ ਪੋਟੈਸ਼ੀਅਮ ਨਾਈਟ੍ਰੇਟ ਭਾਵ KNO3 ਦੇ 5 ਸੈਂਪਲਸ 4.5 ਗ੍ਰਾਮਸ, 5 grams, 5.5 grams, 6 grams and 6.5 grams ਨੂੰ ਵਾਚ ਗਲਾਸਿਸ ਵਿੱਚ ਵੇਖ ਰਹੇ ਹਾਂ। ਪਿਪੇਟ ਦੀ ਵਰਤੋਂ ਕਰਦਿਆਂ ਹਰ ਇੱਕ ਟੈਸਟ ਟਿਊਬ ਵਿੱਚ 10 ਮਿਲੀਲੀਟਰ ਡਿਸਟਿਲਡ ਵਾਟਰ ਪਾਓ। ਹੁਣ ਸਾਰੀਆਂ ਹੀ ਟੈਸਟ ਟਿਊਬਾਂ ਜਿਨ੍ਹਾਂ ਤੇ T1, T2, T3, T4 ਅਤੇ T5 ਦੇ ਨਿਸ਼ਾਨ ਲੱਗੇ ਹੋਏ ਹਨ ਵਿੱਚ ਪੋਟੈਸ਼ੀਅਮ ਨਾਈਟ੍ਰੇਟ ਦੀਆਂ ਵੱਖ-ਵੱਖ ਕੁਆਂਟੀਟੀਜ਼ ਨੂੰ ਪਾਓ। ਹੁਣ ਅਸੀਂ ਇੱਥੇ 5 ਹੀ ਟੈਸਟ ਟਿਊਬਾਂ ਵਿੱਚ ਸੋਲੂਸ਼ਨ ਨੂੰ ਸੱਜੇ ਪਾਸੇ ਅਤੇ ਵਾਟਰ ਬਾਥ ਨੂੰ ਖੱਬੇ ਪਾਸੇ ਵੇਖ ਰਹੇ ਹਾਂ। ਇੱਕ ਬੀਕਰ ਨੂੰ ਬਰਨਰ ਦੇ ਉੱਪਰ ਸਟੈਂਡ ਤੇ ਰੱਖਿਆ ਗਿਆ ਹੈ। ਇਸ ਪ੍ਰਬੰਧ ਨੂੰ ਵਾਟਰ ਬਾਥ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਹੁਣ ਇਹਨਾਂ ਸਾਰੀਆਂ ਹੀ ਟੈਸਟ ਟਿਊਬਾਂ ਨੂੰ ਬਰਨਰ ਉੱਪਰ ਰੱਖੇ ਬੀਕਰ ਦੇ ਵਿੱਚ ਰੱਖੋ। ਨਾਲ ਹੀ ਬੀਕਰ ਦੇ ਵਿੱਚ ਪਾਣੀ ਨੂੰ ਹਿਲਾਓ। ਆਰੰਭਕ ਤੌਰ ਤੇ ਇੱਥੇ 22 ਡਿਗਰੀ ਸੈਲਸੀਅਸ ਟੈਂਪਰੇਚਰ ਦਿਖਾਈ ਦਿੰਦਾ ਹੈ। ਜਦੋਂ ਬੀਕਰ ਦਾ ਟੈਂਪਰੇਚਰ 26 ਡਿਗਰੀ ਸੈਲਸੀਅਸ ਟੈਂਪਰੇਚਰ ਨੋਟ ਕੀਤਾ ਗਿਆ, 4.5 ਗ੍ਰਾਮ ਪੋਟੈਸ਼ੀਅਮ ਨਾਈਟ੍ਰੇਟ ਘੁਲ ਗਿਆ। ਤਾਂ ਇਸੇ ਤਰ੍ਹਾਂ ਜਦੋਂ ਬੀਕਰ ਦਾ ਟੈਂਪਰੇਚਰ 30 ਡਿਗਰੀ ਸੈਲਸੀਅਸ ਨੋਟ ਕੀਤਾ ਗਿਆ ਤਾਂ 5 ਗ੍ਰਾਮਸ ਪੋਟੈਸ਼ੀਅਮ ਨਾਈਟ੍ਰੇਟ ਇਸ ਵਿੱਚ ਘੁਲ ਗਿਆ। ਜਦੋਂ ਬੀਕਰ ਦਾ ਟੈਂਪਰੇਚਰ 33 ਡਿਗਰੀ ਸੈਲਸੀਅਸ ਨੋਟ ਕੀਤਾ ਗਿਆ ਤਾਂ 5.5 ਗ੍ਰਾਮਸ ਪੋਟੈਸ਼ੀਅਮ ਨਾਈਟ੍ਰੇਟ ਘੁਲ ਗਿਆ। ਇਸੇ ਤਰ੍ਹਾਂ ਬੀਕਰ ਦਾ ਟੈਂਪਰੇਚਰ 38 ਡਿਗਰੀ ਸੈਲਸੀਅਸ ਹੋਣ ਤੇ 6 ਗ੍ਰਾਮਸ ਪੋਟੈਸ਼ੀਅਮ ਨਾਈਟ੍ਰੇਟ ਇਸ ਵਿੱਚ ਘੁਲ ਗਿਆ, ਜਦ ਕਿ ਬੀਕਰ ਦਾ ਟੈਂਪਰੇਚਰ 41 ਡਿਗਰੀ ਤੇ 6.5 ਗ੍ਰਾਮਸ ਪੋਟੈਸ਼ੀਅਮ ਨਾਈਟ੍ਰੇਟ ਘੁਲ ਗਿਆ। It shows that as temperature increases, solubility of potassium nitrate increases.
Let's have a look on the table showing test tube, relevant temperature, amount of water in it, amount of solid in each test tube and solubility in each test tube. Students, let's plot a graph between fraction of molecules versus kinetic energy. Distribution curve shows energies among gaseous molecules. What is meaning of this peak point in this curve? Let's try to know. The peak of the curve shows the most probable kinetic energy. It is the kinetic energy of maximum fraction of molecules. If we move towards left hand side of this curve, kinetic energy of molecules decreases and fraction of molecules also decreases. If we move towards right hand side of this curve, kinetic energy of molecules increases and fraction of molecules also decreases. What is the effect of temperature on the kinetic energy of the molecules? Let's try to find it with the help of this animated graph. Students, let's plot a graph between fraction of molecules versus kinetic energy at temperature T. This distribution curve shows temperature dependence of rate of a reaction. Distribution curve shows energies among gaseous molecules. Let's plot one more graph between fraction of molecules and kinetic energy of molecules at T plus 10 degrees Celsius. This graph cut to previous graph at point N. The area showing fraction of molecules at temperature T is also shown here. The area showing additional fraction of molecules at temperature T plus 10 degrees Celsius is also shown here. It is seen when temperature is raised by a value, the maximum point of the curve moves towards a higher activation energy.
Let us discuss about the continuity aspect of activation energy.
K is equal to a multiplied by E raised to the power minus EA upon RT. In this reaction, A is equal to Arrhenius factor, R is equal to gas constant, and EA is equal to activation energy.
On taking natural log of this equation, we get natural log of K is equal to minus EA divided by RT plus natural log of A.
What will happen when we plot a graph between
Natural log of K
and 1 upon T? It is seen that a straight line is observed.
natural log of K1 is equal to minus EA upon RT1 plus natural log of A. Natural log of K2 is equal to minus EA upon RT2 plus natural log of A.
Let's subtract equation 1 from equation 2. We get
natural log of K2 minus natural log of K1 is equal to minus EA upon RT2 minus EA upon RT1. Natural log of K2 upon natural log of K1 is equal to EA upon RT1 minus EA upon RT2. Natural log of K2 upon K1 is equal to EA upon R multiplied by 1 upon T1 minus 1 upon T2.
Log K2 upon K1 is equal to EA upon 2.303 R multiplied by 1 upon T1 minus 1 upon T2. Log K2 upon K1 is equal to EA upon 2.303 R multiplied by T2 minus T1 upon T1 multiplied by T2. What are the units of activation energy? It is measured in joules per mole or joules mole minus 1. There is a question for you students. As discussed above, it is clear to you that collision between reacting molecules is essential for product formation. The Arrhenius equation gives the quantitative basis of the relationship between the activation energy and the rate at which a reaction proceeds. Let's discuss an activity. Let's take 50 ml of 0.1 m Na2S2O3 sodium thiosulfate solution in a 100 ml conical flask and note its temperature with the help of a thermometer. Let's add 10 ml of 1-MHCl or hydrochloric acid to it and start the stopwatch immediately. Then shake the contents of the flask gently and place it on a tile with a cross mark as shown in the figure. We then observe the cross mark from the top and note the time for the mark to become just invisible. We then empty the flask and clean it thoroughly with concentrated nitric acid and then with water. We then again take 50 ml of 0.1 m sodium thiosulfate conical flask and heat it so that the temperature of the solution becomes T plus 10 degrees Celsius. Next, we remove it from the tripod stand and add 10 ml of 1 m hydrochloric acid to it and start the stopwatch. We shake the contents of the flask and place it on the tile having a cross mark and note the time taken for the cross mark to just become invisible. We then repeat the experiment at T plus 20 degrees Celsius, T plus 30 degrees Celsius and T plus 40 degrees Celsius temperatures and record the observations. Let's see this activity with the help of animation.
At temperature 30 degrees Celsius, flask 1 is taken. Let's take 50 milliliter of 0.1 molarity sodium thiosulfate, Na2S2O3 solution in a conical flask. Let's add 10 milliliter hydrochloric acid, HCl in it. Start the stopwatch. It is important to note here that when we add 10 milliliter of 1 m HCl, that is hydrochloric acid, to it, we should start the stopwatch immediately. Then shake the contents of the flask gently and place it on a tile with a cross mark as shown in the figure. We then observe the cross mark from the top and note the time for the mark to become just invisible. We then empty the flask and clean it thoroughly with concentrated nitric acid and then with water. What is the time when mark gets invisible? Mark disappears in 38 seconds. Sulfur is formed as a product and it turns solution milky. Same process is repeated to other solutions. But the temperature is increased every time by 10 degrees Celsius. It means that experiment is repeated at T plus 10 degrees Celsius, T plus 20 degrees Celsius, T plus 30 degrees Celsius, T plus 40 degrees Celsius. Temperatures and observations are recorded. Temperature of flasks 2, 3, 4 and 5 is kept at mark as shown in the figure. We then observe the cross mark from the top and note the time for the mark to become just invisible. We then empty the flask and clean it thoroughly with concentrated nitric acid and then with water. What is the time when mark gets invisible? Mark disappears in 38 seconds. Sulfur is formed as a product and it turns solution milky. Same process is repeated to other solutions. But the temperature is increased every time by 10 degrees Celsius. It means that experiment is repeated at T plus 10 degrees Celsius, T plus 20 degrees Celsius, T plus 30 degrees Celsius, T plus 40 degrees Celsius. Temperatures and observations are recorded. Temperature of flasks 2, 3, 4 and 5 is kept at 40, 50 and 60 and 70 degrees Celsius. Let's plot a graph to observe the results of a chemical reaction at different temperatures. Let's plot a graph between times taken in seconds versus temperature in degrees Celsius. Along x-axis, time taken is depicted in seconds. Along y-axis, temperature is depicted. Look at the blinking point in the shown graph. Students, tell me value of time taken for cross to get invisible at this point and corresponding temperature at this point. Time taken for cross to get invisible at this point is 38 seconds, whereas corresponding temperature is 30 degrees Celsius. Now, let's look at one more point. Students, tell me value of time taken for cross to get invisible at this point and corresponding temperature at this point. Time taken for cross to get invisible at this point is 30 seconds, whereas corresponding temperature is 40 degrees Celsius. Now let's look at one more point. Students, tell me value of time taken for cross to get invisible at this point and corresponding temperature at this point. Time taken for cross to get invisible at this point is 22 seconds, whereas corresponding temperature is 50 degrees Celsius. Now let's look at one more point. Students, tell me value of time taken for cross to get invisible at this point and corresponding temperature at this point. Time taken for cross to get invisible at this point is 13 seconds, whereas corresponding temperature is 60 degrees Celsius. Now, let's look at one more point. Students, tell me value of time taken for cross to get invisible at this point and corresponding temperature at this point. Time taken for cross to get invisible at this point is 5 seconds, whereas corresponding temperature is 70 degrees Celsius. Finally, we see that graph is a straight line.
Let's try to solve a problem based on activation energy. Let's suppose a reaction. A and B reacts to form product. What is the activation energy of a reaction whose rate quadruples when the temperature is raised from 293 Kelvin to 313 Kelvin? Answer is log K2 upon K1 is equal to EA upon 2.303 R multiplied by 1 upon T1 minus 1 upon T2. K2 upon K1 is equal to 4, T1 is equal to 293 Kelvin and T2 is equal to 313 Kelvin. Placing their values, we get log 4 is equal to EA upon 2.303 multiplied by 8.314, which is multiplied by 1 upon 293 minus 1 upon 313. Or EA is equal to log 4 multiplied by 2.303 multiplied by 8.314 divided by 1 upon 293 minus 1 upon 313. Or EA is equal to 52.85 kilojoule per mole. Let's try to solve one more numerical problem. For a reaction with activation energy of 55 kilojoule per mole, by what factor will the rate constant go up with a rise in temperature from 300 Kelvin to 310 Kelvin? Answer is log K2 upon K1 is equal to 55,000 upon 2.303 multiplied by 8.314 multiplied by 1 upon 300 minus 1 upon 310, which is equal to 0.30887, where K2 is a rate constant at 310 Kelvin and K1 is a rate constant at 300 Kelvin. Or K2 upon K1 is equal to 2.04. This example shows that for a 10-degree rise in temperature near the room temperature results in doubling of the rate of the reaction. Students, I hope that you have enjoyed today's lesson 2 as much as I did. See you next time. Till then, bye.